Okay, so let me just admit. Hello, everyone. Thank you for joining us again today for episode 3 of the Carbon Capture and Storage series. So today we're going to be talking about carbon storage, and we have Dr. Branko here with us today, a lecturer from the Department of Earth Science and Engineering, and also a former lecturer for the Carbon Capture and Storage module. So as usual, if you have any questions, just pop them in the chat, and Ferdinand will moderate them for us. And this session is also going to be recorded, and we're going to put it up on our website that we're currently working on with Grantham. So with the interest of time, I'm going to hand over to Dr. Branko.
Thank you very much for inviting me. In the interest of time, I'm going to start immediately with telling you what is the purpose or what are the ideas that I would like to remember after this relatively fast lecture. So you can see the clean fossil fuels. This is the idea that I'm going to pursue. Why? Well, that's the current situation. More than 70, 75%, 80% of total energy needs are basically provided nowadays with the clean fossil fuels. If we are to change this with renewables, it's going to happen in this century, but it's not going to happen, immediately. So we need a transition period, and these are one of the solutions that would help us overcome this crisis that is been developing over the last few decades and now becoming more relevant and imminent. So I will start with describing what the carbon cycle is, what the human impact is on it, and how is that related to the population and peak oil, and what are the solutions of using fossil fuels in the foreseeable future in combination with storing these CO2 emissions underground. That is carbon storage. So what are the big questions in this century? Basically that we have, I'm going to skip learning objectives again in the interest of time, but the big questions in this century are all related to the population, and population needs food, water, and energy. So all this is intertwined, and it will define not as least our standards of living, but also the population growth and sustainability on the planet. So let's start with global carbon cycle, continue with population growth, and see how these energy needs are satisfied by fossil fuels, and talk about oil reserves, fossil fuels reserves in total. Population, fossil fuels and peak oil, and carbon storage as a solution, as I just said, all come to the global carbon cycle, impact of humans. The top is the equation that carbon dioxide plus calcium silicate goes to carbonates and silicium dioxide, which is sand. This is inorganic carbon. The bottom equation is carbon dioxide plus water, organic carbon plus oxygen. What I want you just to remember, without going too much into details and all this complicated sketch, is that these equations are normally working on the time lengths of the thousands of years. However, since the times of Industrial Revolution, which is 1783, induction of James Watt, we started burning this organic matter that we exploit as in the form of fossil fuels. We burn it with oxygen, we create carbon dioxide, which gets emitted into atmosphere, water plus energy. That's why we disturb global carbon cycle from right to left in equation 2, accelerating it 100 times. This results in a significant increase in carbon dioxide in atmosphere. And if you look back over the last 1,000 years or so, because some people will say, if you look at this middle curve, this is Charles Keeling curve, which is basically measuring an isolated place, such as Hawaii atmospheric CO2 concentration. We see that this concentration is increasing and currently is between 415 parts per million and 420 parts per million. So there were some comments saying, come on, if you start from zero, that's very little increase. No, the answer is we don't start from zero. We start from, say, times pre-industrial revolution, because this is where the change suddenly started to happen. 1750, 1783, we started exploiting fossil fuels, which increase by at least 2 or 3 ppm parts per million per year atmospheric CO2 concentrations, resulting in greenhouse gas effect and obviously resulting in a climate change. People did know about this in the past, and they foreseen this as a problem. Calculating for this, now it's almost like abundant. This is 2004, and this was calculations that led to how much cost in trillions of US dollars would be needed to preserve atmospheric CO2 concentration at 450, 550, 650, and 750 parts per million. At that time, I think it was concentration was 370, 380 parts per million. Nowadays, it's already 415 or 20. So we are approaching this first landmark concentration of 450. So the idea was the Kyoto Agreement, before Paris Agreement, which was actually signed by many countries in the world, to keep the concentration of 550 parts per million. Yet we don't know, we're still going into an uncharted territory, and we don't know the consequences on the climate change. So, but to do so, up to $10 trillion, you know that $10 trillion is about half of the gross domestic product of US or China. And if you're to keep it at 450, it ranges up to 18 as of the full gross domestic product of the largest world economies. So this is the problems that we are facing when it comes to cost for stabilizing CO2 concentrations, and you guys will help us do these calculations properly. So let's continue. What does it mean? These carbon dioxide concentrations come from fossil fuels up to this red line. This contribution is by oil. From red line to green line is the contribution to gas, from gas. From green line to the solid line is the contribution by coal. And this was up to, say, 2005. You can see that in the future now, currently 2020, we still increasingly use oil, gas, and coal. Half of the CO2 concentrations emitted by coal, gas, and oil have been taken by the oceans. So actual atmospheric emissions of CO2 are double of what we show on this graph. What I want you to remember that most of future increase in CO2 atmospheric concentration would come from coal. And that was the situation also in the past. And this is something that we can do just by switching from coal to gas and oil. We will be able to dramatically decrease this curve on the increase of carbon dioxide concentrations. So let's see, how is that related to the population growth? What are the parameters that we are looking at? Well, what we can see here is the world population in, say, millions of people. So you're talking about 1 billion people here, and you're talking about over 7 billion currently in 2020. You can see that by 1999, the world has reached 7 billion people. If you look at this as population versus time, you could see that world population was pretty flat until we started to discover big discoveries in terms of food production and in terms of health. So the lifespan has increased, and so did the population growth. So we seem to be growing exponentially in terms of population. To describe this, I won't bother you with all these equations, but just remember there are two types of models. One is the constant growth rate. So this growth rate is inverse of population, and then you have some change in population over a period of time. This leads up to an exponential increase in population, and you can calculate time needed to double the population. So if population growth rate is 1% and it's constant, it takes every 69 years. If it's 2% only, it doubles every 35 years. So if the population growth on this planet was 2%, in 35 years, which is your lifespan, we would have had 14 billion people, or even 15. However, the situation is better. If we now plot population growth rate versus here, we see that this growth rate G is never constant, up and down. You can see some estimates here that there is a plague in the medieval time, there is a Chinese famine, and then we actually see that it's never been constant. It's going up and down, but recently seems to be going up. So to see this recent period, we will plot it as population growth rate versus population numbers, not year. And we see that here, that in 1963 we had a maximum growth rate, which is called demographic transition. After this, the population is still growing, but it's growing at the growth rate which is decreasing now. So if we now start to linearize this equation, we will somewhere hit, we assume that this behavior will be followed in the future, we will hit somewhere the x-axis. Where we hit the x-axis, this is this maximum population. There's as much oxygen in your room now to fill in how many people. There is as many people on this planet that the planet can sustain. So we're thinking about hitting this with linearizing this behavior. And we see that if we do that, there will be a slope for that curve, which is equal minus r over k. And we will hit somewhere around 10 billion people, 10.2 billion people. And now we have another equation. Do you see this part of the graph? Okay, I'll move it here. At least on my screen, this was not seen. So now we have assumed that the growth rate is no longer constant. It's actually decreasing in future. And it's equal R, which is growth rate for the small populations, where I hit the y-axis here. That would be my R. And then 1 minus P, which is population time T, over K, which is carrying capacity of maximum population. So look at this. If I have my population that is very small, my P would be much smaller than the maximum population, which is K, of carrying capacity, right? So my very small number, divided by a very big number, would give me 0. 1 minus 0 is 1. So my growth rate would be equal to R. So if P is close to 0, I'm on the y-axis. Wherever I hit the y-axis is this R, or growth rate for small populations. If, on the other hand, my population in the other limit approaches K, which is maximum carrying capacity, my P is almost equal to K. So 1 over 1, the same number over the same number is 1. 1 minus 1 is 0. R times 0 is 0. My growth rate is 0. My growth rate is 0. I hit the x-axis. And this tells me that if things happen in the planet as before, I would hit around 10 billion people later this century. Now, there's this logistics equation, which is just explained, and then these are the limits that I was talking about, right? If P is much less than K, growth rate is R, growth rate for small populations. If P equals K, growth rate is 0. And that leads us to this situation where we have no longer an increase in population. So if you apply this logistics equation model, you will see by the end of this century, we will asymptotically approach somewhere around 10 billion people. So this is expectations when it comes to the population growth. Okay, so you got it. Now I'm going to talk about how the same models for the population growth could be also used for estimating the peak oil production. What did we say? The growth rate is equal growth rate for small populations, 1 minus population, divided by maximum population of carrying capacity K. So this is the situation in population biology. Population, rate of population increase, growth rate and carrying capacity of maximum population. Drawing parallel to the oil production, we can say that population is now cumulative recovery up to a year, say 2020. And then we have delta N over delta T. If we take delta T as a year, that will be oil production in year 2021, for example, that we would like to predict. Then we have a growth in production rate, which is equal to this growth rate for small populations. And then we have total oil of ever recovered, all oil reserves, which is the maximum population, right? Or maximum oil ever recovered. This analysis was done by King Hubert in 1956. It was at the time, as you will see in a moment, where the oil production, I will skip to here, was increasing of conventional oil in US in a way that people are very happy. They always thought that this will only go up, but you guys study business and you know what goes up also goes down, only to recover later. So basically, what we are going to do now is study or predictions of King Hubert done in 1960s to what is going to happen to the US oil production of conventional oil over the years to come. I will go back now. Assumptions are oil is a finite resource. There's only as much conventional oil in the US as you can get. It can increase over time due to new discoveries, but it's not going to be infinite amounts. Oil production started at some point in the past, initially underwent exponential growth. And then this means that oil must peak at the same time and start to decline because there is only a limited amount of conventional oil. This is actually also related to any other resource. So not just to the peak oil. You can have everything the same and similar to, say, lithium. You can have for batteries. You can have similar things for any other elements needed, for example, nuclear energy, plutonium, and so on. And in fact, Hubert also did predictions for that in 1956. So what did he use? He used this, what we already knew, R times 1 minus NT over K. This is just written in a more plausible for you form. And because of that, we know that NT is the population or oil that has been recovered up to this year, 1960. And then delta NT plus 1 is the oil production in the next year. So if we plot delta NT plus 1 divided by NT, we will get the logistics equation. And that logistics equation will look like this. We will have to get this linearized as we did with the population. So we can draw several lines, and whatever this actually is a middle prediction, we discard this early data because it doesn't make much sense to the later data. This is a much higher production because it's initial. Obviously, small numbers do carry some risks when it comes to analysis because going from 1 to 2 is not the same than going from 10 to 11. And we are going to hit 200,000 million barrels, so 200 billion barrels of the cumulative production over time. And what King Hubert predicted, and I'm not going to bore you with all this, this is another method, but what he predicted is this solid line here. So the solid line is showing you that there is a peak, and this is, look what happened in this larger peak because of the oil crisis dip here as well, 1970s. But it actually quite well predicted, is one of the best predictions when it comes to business model of what actually happened. And now you see that the conventional US oil production is decreasing. If we do now US oil production with fit, we have seen this graph already. We have these parameters R and K. This is now the maximum oil ever recovered. So we see what happened since 1960s, and we added now this part, and we nicely see that in 1994, for example, this was following this slightly higher because of new reserves, but actually quite well. What was the change maker in the 2000s was the discovery of what we call tight oil, but this is called, remember, tight oil is unconventional oil shale, which has not been really normally counted as conventional oil. And you can see that contribution was very low until 2010 or so, when it started to increase and become very significant. So the US started to become net exporter of oil. However, you can see that conventional oil, which has this green, red, and blue color, Alaska offshore and onshore extraction, it has decreased over time. So this is this logistics equation decrease, but the situation has been changed by unconventional oil, which was added to the picture. And this is what we call, this is the prediction of logistics equation, which was followed well until the unconventional oil started to increase the oil production in US. So we call this as a second wave. Obviously, eventually what's going to happen, you only have a limited amount of this unconventional oil as well in shales. So eventually there will be a second peak and then it will decline again. Obviously, there are also other economical factors which impact the production, which is the price. And now we see that once we added this red here, we started to stabilize at that time. Red was unconventional oil. If you produce more than what market needs, you're going to keep your price down. And this is exactly what happened to the price of oil. 2007, the oil price was $120 per barrel. That was quite unbelievable at the time. But if you think of what you have with oil, it's the largest energy density per unit volume. You know, imagine in the past, you put the coal in your on your train, and the guy was making a lot of, you know, adding on to this to create steam, and you would end up in Scotland in what, you know, like a few days time. Nowadays, you just put 10, 15 liters, 20 liters of petrol, you're in Scotland by, you know, half a day or less. So this is this energy per unit volume density that is highest with oil, less with gas, less with coal. And that's why oil is so important. And I have to say, oil has actually improved the standard of living of many people like nothing else being done. So what do we have now is the situation where we kind of round up on oil companies and say, you emitted this CO2. Actually, they did produce fossil fuels, but that was for the people, and people spend these fossil fuels, and that's what caused the emissions. So what the timing now is to help oil company transition from producing less fossil fuels. They are still needed because we don't have this other source of energy, and help them transition to renewables and still produce some of the fossil fuels, supported by carbon storage. So that's the solution that is the most realistic. Otherwise, if we just stop having this energy from fossil fuels, we will lose so many jobs that it will be very difficult to control the economies in the world. So we're talking now about logistics equation predictions for the population on the planet. And again, we see some early data noise, but since 1981, we see actually very, very linear decrease in behavior like the logistics equation would predict with this minus R over K slope. So we end up with R here of 0.05 per year, and we have 2.4 trillion of oil to be produced. So this is now for the world. So this is for the population for the world. So the world's population would need to consume this conventional oil by 2.5 trillions of barrels in this century, if you want. So because we are still producing these fossil fuels, we emit in CO2, and that's our real problem. When Hubert predicted this for the world, he looked at the oil peak in 2010. This did not happen. Oil peak would happen later. And this is another study that nicely shows that as we have more discoveries, then we will have still finite reserves. But on the other hand, we'll shift the peak to a later date. So 2034 in this ultimately recoverable oil reserves of 4.5 trillion barrels. In comparison to 2 trillion barrels, which was initially predicted by Hubert's analysis. So I will conclude now the first part. I'm going pretty fast, but humans have exerted the greatest impact on the carbon cycle since the Industrial Revolution. 100 times accelerating, disturbing the global. The planet cannot take it. Because of the population growth, we have to think about the issues when it comes to energy needs and use of fossil fuels. We looked at the models that show the constant population growth. They never actually materialized throughout their history. So we looked at the constrained growth by basically logistics equation, and then concluded that the population would grow to 10.2 billion people. And then there will be oil production that would peak, I mean, last slide showed 2034, doesn't matter, but sometime in this century. So we need also alternative sources of energy. However, until we get to that, we still need fossil fuels in the energy landscape. An energy mix has to have them. So this would be the first part of my lecture. I'm happy to get some questions now, if you prefer. If not, I will continue with the second one.
I have one question, if you don't mind.
Absolutely.
Dr. Bijeljic. It's on your graph showing showing population growth that hits the x-axis at 10 billion, but there's a red dotted line that hits earlier. What is the red dotted line?
Coronavirus. No, there are some doomsday scenarios, and we could be, various issues on the planet, and that would actually also include this killer disease. And this was one of different scenarios. But so there are various scenarios, but this is just a prediction by logistics equation based on the past history data. Obviously, we cannot completely predict what's going to happen in the future. Nobody actually was predicting when viruses like corona would happen. So this would certainly have some. And I have several graphs that show you also these predictions on individual countries. So, for example, I don't have them right now here, but it will take us time and we need to go within an hour. But I can give you a monograph that tells you, for example, how population growth changes over time in the US, in Saudi Arabia, in Rwanda, for example, as this very bad war which happened there, and how did that alter the population growth. And all of that is actually subject to social component as well, and also biological components. But we need to have some predictions which are relatively firm, I have to say, unless, we could also be hit by a meteorite and things can change, but there is a very small probability to do so.
Thank you.
Okay, so shall we go next, or do we have another question?
Could I just ask a question quickly about how do you sort of go about determining the growth rate of, say, a commodity like oil? What are the factors that affect that?
How do we go about determining growth rate? I mean, I've just shown you there. We assume that there is a, but fair enough, I will bring it back. I know I'm going too fast, and this is in the interest of time, but let's get to, we start from here. So you see, these are the data that we are working with, right? And we discard this initial here because it's obviously not giving you any meaningful extrapolation. And normal, as I said, initially you produce much more in a shorter period of time because you started from a very low number. If you go from 1 million barrels to 2 million barrels, that's 100%. But if you go from 10 million barrels to 12 million barrels, that's only 20%, although you actually produce more in the second case than in the first. So we discard this part here of the graph and we only use it something that extrapolates here. So if we plot this delta NT plus 1, which is production in 1 year, which happened in the past, right? All these solid line data. For each year in the past, we have production of US conventional oil. So we have that data. We divide it by NT, delta NT plus 1 divided by NT, and we plot it on the y-axis. NT is total oil recovered up to that year T, right? And this is up to 1960. So all of this year's productions is NT, right? And now delta NT plus 1 over NT is R, 1 minus NT over K, yeah? So now we estimate R, where we hit the y-axis, and we estimate K, where we hit the x-axis. So now we have R and K. And now we predict delta NT plus 1 based on what we know, which is now R, K, and NT. So we know that data on the right-hand side of the equation. We now know delta NT plus 1 by calculating it from here. Now, when we know delta NT plus 1, so if I started 1960, I know the production in the world up to 1960. If I want to know in 1961, I will calculate R I know from this graph, NT 1960 I know, K I know, NT I know. Now I calculated delta NT plus 1. Aha, I can now know NT plus 1, right? Because I can add delta NT plus 1, which I calculated, to NT. And so I add for N in 1961, I calculate as N in 1960 plus delta N 1961. So now for delta N 1962, I do the same, but N is 1961. For delta N 1963, N is 1962, and so on. So this is how I predict all the production in the future.
Yeah, thank you very much. I think I was more kind of wondering as to, so in that time period where this historical data was collated, oil was effectively a very essential resource. So there wouldn't be much rationale for the demand of it or the necessity of it to change. But then going into a world where there's potentially going to be legislation against oil production, what effect will that have on the growth rates that are used to kind of calculate these peak oil productions?
Sure, this would affect this because we can artificially impose anything on this curve. This is just like unabated, you know, like it was driven by the market as well. I showed you an example of unconventional oil and how it changes price, but it's also energy needs of the people. You know, the larger population needs, the larger energy needs. So this is all going to have an impact. If we want, you can see how it actually was developed here up to 1994, pretty much through the middle of the curve. But what's going to happen in the future, we can influence. You are right, absolutely, we can influence. It may decrease, but I wonder by how much in the near future, because we don't have an alternative source of energy.
Okay, thank you.
Okay, so in the interest of time, I don't want to, get you here like a fast train through everything. So I'm going to continue. So don't worry if I skip something on the slide. I will still give you the main ideas of these slides. So what are the main, we will not go into calculations, of course, but now when it comes to clean fossil fuels and hydrocarbon reserves, we're asking ourselves, okay, how much of these reserves there are in the world and what would be the carbon dioxide release potential? What can we do about storing this CO2, which otherwise would be released into atmosphere? So this will be talking about CO2 storage in the subsurface and trapping. So we'll skip this. We'll just go for oil reserves. What does it tell us? Potential for liquid hydrocarbon production is enormous. The dark green is the reserves which are certain. The bright green is increasingly uncertain resources. So even if we take just certain reserves, we could see that so far we spent 1 trillion of liquid, 1 trillion barrels of liquid oil. And now, if we are having to spend in the future another 1.2 trillion barrels, this is this part here, that's going to emit another, how much of CO2? If we now include enhanced oil recovery methods, that's going to bring us another significant volumes of oil. If we look at tar sands in Canada, heavy oil, and so on, we can have another significant volume. Gas to liquid steam fuels, coal to liquid steam fuels potential, and oil shale. So you can see that we can at least 10 times more spend of the oil reserves in the future, and that will not happen, I can assure you, because we will emit so much CO2 that it will ruin the planet completely. So now the question is not how much of this energy resources we have, what do we do with them in a wise way? So oil production is here given like 80 plus million barrels per day. It is not a problem, global volume, it's environmental consequences that are problems. And if you look at the numbers in oil production, you may find very interesting that if you have a major giant oil field, single field in Guar in Saudi Arabia, is responsible for 7% of the oil production in the world. 50% of the oil production comes from the largest 100 fields. So this tells us that this is quite controllable, right? The oil production is quite controllable. So what we see here is when we discover oil, we find normally the largest oil first. Why? Because there is more probability to hit that. It's more likely. And we see that from 1900 to 2000s, most of these conventional reserves are already being discovered. Their new discoveries are in decline. Oil production rate can be increased. For example, initially we recovered this much oil, but we have different technological techniques, methods that can extract even more oil. How much oil per person? This is something you'd be interested in, because this is actually this crosses here through the past, through the history, and we can see you see, as we grow the population, if we don't follow that with the same oil production, we end up with a decrease of oil per person on the planet. And it's very uneven, of course, as you know. Developed world spends much more oil per person than undeveloped world. And that's another big question for the future. But you could see the 1970s, that was the peak already, and now we're only going down. So we're asking ourselves, how much oil will, when we burn all oil reserves, how much CO2 will be emitted into the atmosphere? And I won't bore you with the calculation, but we assume that oil is heptane, which is just a C8, basically H18, and plus oxygen gives you carbon dioxide, water, energy. So how much carbon dioxide will be emitted? We can calculate that, and in the moles, so we can see that we have 10.7 times 10 to 15 moles if we burn all 1.2 conventional oil reserves. The same we can do for gas. Again, we won't go into details. This is a gas state equation, and we have 7.6 times 10 to 15 moles. And now we calculate the total number of moles in the atmosphere. We assume that just for the sake of calculation, the Earth is spherical. We equal by Newton's law the forces at the Earth's surface. We have there a diameter of the Earth, 6,380 kilometers, and we have gravity acceleration, and we have molecular weight, which we take as mostly nitrogen, because it's 80% nitrogen, approximately 20% oxygen, and we arrive at this number. So what's important when we divide now the total number of CO2 released by oil reserves, total oil reserves, divided by total number of moles in the atmosphere is 57 parts per million. So this is the addition. As I said on my graph previously, half of this will be uptaken by the oceans, half of that will go into atmosphere. For gas production, we have slightly less, 41 parts per million. And then if you go back to what I said, so oil and gas. Now with coal, we will have the largest contribution, be it anthracite, which is high carbon content, or lignite or substitutes with low carbon content. We will now have an order of magnitude almost larger number of moles emitted from burning coal reserves, which ends up as around 300 parts per million. So it's actually 3 times more than oil and gas together. So the largest potential for global warming comes from coal. So how do we sort it out? We sort it out in a way that we can burn fossil fuels, but we need to emitted CO2 collect, transport it, and store it under Earth's surface. So this is the idea of carbon storage. And now, just briefly about carbon storage. We have a large potential to store many gigatons of CO2. The emissions are around 35 to 40 gigatons. They went down now due to Corona. So you can see that an annual emissions is 35 gigatons. Only in aquifers, we can have up to 920 gigatons. So in oil and gas fields, whereas in aquifers, you can get to up to 10,000 gigatons. And in the North Shore alone, we have a lot of reserves when it comes to carbon storage. Especially because a lot of oil and gas fields, they are maturing. So now is the time because we have infrastructure there. So what did I say? I collect CO2 at the point source, which is, for example, power station. And then I transfer it to the point of injection and inject into ground. When I inject into ground, subsurface, it goes deeper than 800 meters. And then the CO2 is a complicated story, but you need to know that CO2 in its own phase, this blue color here, would try to rise to the top because it's lighter than this water or brine in the aquifer that you injected to. So due to buoyancy forces, it starts to rise to the top. And now the design of the process there revolves around how to keep that CO2 in pore space. So these are CO2 blobs in this pore space, which is green here. And black is pores and blue is the CO2 in the middle of the pores. So the idea is how to make that CO2 residual. If you inject first CO2, then inject brine, which catches up with the CO2, surrounds it by capillary forces, keeps it fixed in the pore space. So your CO2 does not come back to the surface. Some of the CO2 will be dissolved in water, and this is this light blue color. If it dissolves in water, brine, it will be heavier than in situ brine. It will go down, sink down the reservoir. So these are the mechanisms. The last mechanism would be a chemical reaction, but more about that later. And here we have, which will be interesting, carbon storage in deep sedimentary basins around the world. So I'd like to actually do this next slide. Point sources, previous slide, sedimentary basins. So if you look at that, actually they are pretty close to each other, one another. So the transport would not be very costly. So this is the carbon transport with infrastructure in the UK. Carbon dioxide properties, just remember that supercritical CO2 we are talking about once we inject it. So the good thing is, as you can see here, is that you have, we'll have to move this up. The good thing here is that you have a lot more volume of the CO2 if it's on the surface. But once you inject at the high pressures and temperatures, this volume gets squeezed. So that's very good. It's got different properties than normal CO2. The bad property is that it's lower viscosity, so it actually flows better, which is we don't want it to flow, we don't want it to escape. And then we have also now a slide on some numbers just to illustrate these current emissions, which I already mentioned, around 35 to 40 gigatons per year. And because of this supercritical CO2, we need to inject a lot of volume of CO2. So this is basically to achieve 1 to 2 gigatons of carbon per year. So in fact, this is just to make you aware that the whole industry of the size of oil industry or gas industry is needed to perform this carbon storage. This is prospective aquifer storage sites in North America. This is gas and oil storage. Don't think that aquifers, we are taking fresh drinking water. We are actually taking only saline aquifers, which is water that is not for drinking. This is capacity in the North Sea, and you can see various capacity in oil, maturing gas and oil fields. And now infrastructure is also needed. This is an interesting slide for you, the storage capacity. So first you start with this theoretical capacity, which is basically you estimate how much CO2 you can store in place, but then you need to apply different cutoffs, such as geological engineering cutoffs. It's not very convenient to put it in certain parts in the subsurface, so the pyramid becomes smaller, the volume. And then in the end, you have viable capacity, which applies economic and business case to the profitability of the whole process. By the way, profitability is only possible if we have carbon tax, in my opinion. We need carbon tax to be able to do so. And if we don't do that, there will not be driver to do CO2 storage in the subsurface in the large amounts. So I was involved in UK storage appraisal projects with the Energy Technology Institute, in which we basically assess CO2 storage potential. We identify many units. There is a very nice database that can tell you has different storage units here. And basically the capacity was large. I mean, 60 gigatons plus, So we have quite a lot of capacity in the UK. I just wanted to mention to you, although you don't want much of the technical things here, I already mentioned the situation that happens when CO2 is injected, and I explained everything, including this capillary trapping. CO2 in its own phase rises to the top, wants to escape. So here is the situation. You inject CO2, it can go back to the injection well. That's my first escape route. Then it can go up deep because of the buoyancy forces. It goes back to the surface. It can also move into a different formation, which we didn't know it was linked to the information that we injected to. It can diffuse through the cap rock. Cap rock is very impermeable here, doesn't allow CO2 to escape, but if integrity is jeopardized, that by diffusion it can still escape through an abandoned well that we are not aware of it and we didn't cement it. And this is compartmentalization or by fractures or faults. So we were not aware that there is another compartment part of the reservoir which is conductive, and then it escapes through this route. This can also change if you work in an environment which is prone to earthquakes. So we don't want to do that. It will also increase the pressure in the reservoir once you inject CO2. So what we do normally, we inject up to 90% of the maximum pressure so as not to create these faults due to additional pressure in the reservoir. And how do we design the CO2 storage? What did I say? We first inject CO2, it's underground. Then we inject chase water to trap that CO2 by capillary forces. So this is actually now a study that shows that this is this trapped CO2 saturation, which is most of it in the reservoir. This is the mobile, which is much less. These are the current CO2 projects. A very brief overview of the projects, loads of them, but they are very small. That's the problem. Successful projects include Norway. That's the first ever Statoil was incentivized by not having to pay a tax of about $55 per ton. Norway imposed at that time on CO2 emissions. I think it's no longer in place. And this was injected 1 million ton per year since 1996. It's very successful. Actually, it's been followed. The plume's been followed, as you will see later on. Second one is a Weyburn oil field in Saskatchewan, which was between US, who supplies CO2, and Canada, which injected CO2. So this is the Sleipner project. You can see how CO2 is injected into the formation. And then the plume is then started to be followed, as you can see here, starts to rise to the top. And now you must do seismic tracking in time and study plume migration. So the other thing is the ownership of the field, which has to be agreed in advance, and also over many decades, because this is going long into the future. Here we have another example, the Insala project in Algeria, in the desert. So again, 1 million tons of CO2. Here, there was a problem with the subsurface, with the surface uplifting, and that created some additional problems. So it doesn't go without constraints when it comes to injection. If you overdo with the injection pressure, you may get surface uplift. And another small project like in France, very deep, basically I think it was up to 4.5 kilometers up there, and small amounts which was just for research purposes, but it was very successful. So to conclude, in this part of the lecture, we looked at the potential for the liquid hydrocarbon fuels to ruin the planet, let's face it. I mean, if we spend all that and if we emit that CO2, the planet would not exist. So we need to apply constraints to our not only production, but consumption. As I said, if we constrain consumption, we can deal with the problem. If we attack oil companies, that won't solve the problem if we still need to do that consumption. There is a balance to be made in the future. Now, we also have a big price to pay if we continue to use coal over gas and oil. And this would increase the CO2 atmospheric concentration much faster. We estimated that, and I showed you how to do that. Then the technology that could play a significant role, apart from the renewables mix, apart from the nuclear energy mix and so on, we need to use carbon storage because we would need in the near future to use over the next few decades fossil fuels to keep our economies and jobs going, and that could be done successfully by looking into carbon storage. And we looked at this proven technology, I would say, at the smaller scale. So far, we understand the processes. I didn't mention it all, but we've done a lot of research in my group at Imperial, and my collaborators. We are pioneers of understanding all these physical mechanisms of CO2 in pore keeping CO2 in pore space. So we know how to do it, but we need incentives, and especially oil companies, gas companies, and so on need incentives to do that. And that should come from carbon tax, in my opinion. There used to be at times, about 10 years ago, when we had carbon trading options and futures, and that disappeared because the quotas which were given by the countries were not respected. And we are back to square one, and yeah, it's up to us how to solve the problem right now. I've been talking about this since 2005, but only in the last year or so, I see some serious movement to resolve this situation. Thank you very much. I'm open to the questions.
Thank you very much, Branko. I think that was super informative. There are just a few questions here on the chat. The first is from Leopold. Are you able to ask your question?
Oh yes, thank you, Ferdinand. I was just wondering if you could give us more explanation on the graphs regarding oil per person, consumption of oil barrel per person, the middle of the lecture.
Sure, I know where it is. It's just I have to get it faster to there. Thank you. Yep, we're here.
Yes.
Okay, so forget about red curve. That's just oil price. And you can see the oil price was very high in the 1980s when the oil prices was there, especially the nominal price. This solid red curve is the nominal price, but this is the price in today's, accounted for inflation. So they go asymptotically match each other in recent times, of course. So this is how the oil price increased, but you could see this was caused by different issues related to the I would say geopolitical impact at the time. How many barrels per person we produce? That's the question we're asking ourselves. In 1950, it was 1.5. By 1970, we had 5.5 barrels produced per person per year. Ever since, because our production did not increase as much as our population increased, think about it this way. Population growth every year is around 85 million people. That means that every 12 years, we're increasing our population by 1 billion people. So if 6 billion people were in 1999, if I'm correct, then add 12 years by 2011, we were on 7 billion people. By 2023, we would be on 8 billion people. So, okay, we know that the growth rate is decreasing, so it's not as much, slightly less possibly in the future after that. So the point I'm trying to make is that the population is growing much more rapidly than what we adding oil. So that's why we're decreasing this number of barrels produced per person. And that's really, the solid line was a kind of a prediction that is, as you can see, very approximate. But it's possible that this would further decrease as it did in 1980s to 1990s because of the several factors. And one is first population growth, which is not followed by increase in oil production. The second one is we decide not to produce as much oil. I would say, not leaving it to economy to decide, where we politically decide that this is not good for the planet, therefore we produce less oil. So the implications are, and I'm not advocating only oil here, I mean, there is all other renewables that we have to use in the near future. I am advocating transition from, we cannot, in my opinion, do abrupt change. We are not ready for it. But over the next 10, 20, 30 years, we could do significant change to become less fossil fuel intensive society.
Thank you.
Okay, so our next question is from Annika.
Yes, thank you very much for the talk. I was just wondering, are there ways to measure the success rate of the carbon storage? How could I know if really 100% of the pumped carbon, the pumped CO2 is stored, and how can companies be held accountable on how well they're actually doing it?
That's where lawyers will come in. Basically, you have to have the ownership of the field, and obviously who will be liable. I mean, again, companies come and go. What will happen in 50 years' time and what will happen in 100 years' time is that this CO2 will still have to be there. And who can commit for 100 years period? So in my opinion, this has to be solved through the governments. There's no other way, because you've got companies that exist nowadays, but in 50 years may not exist. So that what happens to the ownership of these fields? So that's an issue. How do you measure success of the CO2 storage? Well, you follow this by seismics. I just, I think I illustrated this through the, I think it was, where it was, yeah. So you follow this basically by seismics, and you follow the CO2 plume, and you basically expect that all of that CO2 would be safely stored underground, and you do engineering design so as to ensure that, such as this capillary trapping by injecting water. What happens if 5% of that CO2 leaks? Well, it's still better than 100% of that, which otherwise would be in the atmosphere. So 95% of that would be there. That's the first argument. The second argument is, of course, that leak could be problematic when it's onshore, when there are people obviously living nearby. So the suggestion is then that we first start with the offshore projects in the deep sea, in the sea, so that we don't have direct environmental consequences once we start to inject significant amounts of CO2 in the subsurface. Next question.
Branko, do you have time for 2 more questions?
Absolutely.
Okay, well, Lucy, do you want to ask yours?
Sure. You had a map that showed the UK infrastructure for carbon capture and storage. If you don't mind showing that. And I just also would like to ask if we can import CO2 and store it in offshore locations, and how would that work with the shipping routes?
Yeah, I mean, you're absolutely right. If we can have this as a business opportunity, but a lot of things must happen before this can be materialized. So we do have capacity. We have over 60 gigatons, 70 gigatons. There will be countries which won't have this capacity, yet will have to emit CO2. So if we have a system in which tax the CO2 emissions or carbon trading of CO2 emissions, they could be tankers going to these countries, bringing that CO2, injecting it into the North Sea. So now this is one way of how to do it, but the infrastructure, some of it is existing, but some of that would have to be built. The problem with the infrastructure is that a lot of this infrastructure is already in place, but for mature oil and gas fields. So they're towards the end of their cycle. If we abandon them in 10 years' time, we will have to start from the beginning and put all new infrastructure into it.
Okay. Did you have another slide that shows the actual UK pipelines and infrastructure?
Yes, I did. Let me just see that here. Yeah, absolutely. So this is the just
That one.
say that transport onshore would go through the pipelines, and hydrocarbon pipeline corridors already in place in much of the US and the UK. But intercontinental transit is by tankers. So, but again, this is on land. But what happens offshore? Because we have to get it offshore as well.
Thank you very much. Yeah.
With all respect, but people don't like the idea that you inject CO2 under their houses. And this was actually one of the early mistakes made in the Netherlands, where they started doing that near the city. I don't have to say which one, but there's a lot of bad reputation that came to CO2 storage after that. And hey, when you start doing it, you don't do it, in the near where people live. You do it offshore somewhere in the seas, and then you study it, and then you see how many more projects you can make. So, some of the things were not done properly in the past, but we could actually start doing it with the government international incentives.
Thank you.
Next is Ying Ying.
Yes, thank you. Thank you, Dr. Bijeljic, for the presentation. Actually, my question is quite relevant to the last point about international collaboration. So, although US, North Sea, and Australia are large producers, but so far, I think globally, Middle East remains the biggest producer. And also the cost of producing in Middle East is much lower than elsewhere. So all these countries, they have not as strong governance structure as the OECD countries. So in this sense, it's how we can make sure that the emission from all these producing countries in emerging market can be decarbonized, like what we are doing in the North Sea. Is this has been discussed in the sector?
Sure. I mean, yeah, you're talking about, say, oil gas producing countries, which have a very low cost production cost, and therefore are likely to continue significant amounts of production in future.
Yes, and also they don't have a stringent carbon system like Europe or maybe North American is going to have.
Sure. I mean, they have to either build a system or transit by tanker, but the whole point is that you have an international system of carbon tax and trade, in which case, it becomes for them profitable to, if you have a tax of say $60, $70 per ton, and if the cost of getting rid of that by tanker is $30 per ton, they would make a lot of sense for them to do so. So this is my suggestion, that we have to have a system which would be basically low on international at the international level.
So it's more like a border carbon tax.
Carbon tax and trade system. I mean, trading emissions, I think, would then make it profitable for the companies to do it and governments to do it in a proper way and without any arguments, like, why would I stop my production where I produce less per capita than other countries that produce per capita, but then the other guys say, but you produce more as a volume, and so on, so on. It goes forever. I think we need a very mature international system that would solve this climate change problem of CO2 atmospheric emissions. And I can't see any better way than carbon tax and trading.
Thank you. It's just because I have been working for commodity companies before, and all the physical commodity flow, there's a lot of dodgy stuff happening behind the scene. So I'm just thinking in terms of looking out the outlook of the future market. Is it really possible that we can have a highly efficient global carbon trading or carbon tax system that can avoid any leakage
Carbon tax was only deployed individually in some countries, such as I said in Norway, there was a carbon tax in one period, which incentivized companies such as, at that time called Statoil, nowadays Equinor, to perform this first CO2 pilot project. What's going to happen is that you must have this, I would believe, a trading system in which you are going to balance all that. So again, I'm back to this argument that it's commodity, as you say, as any other commodity, but it's actually saving the planet. So it's got to be taken with the utmost importance.
Yeah, thank you.
Thank you, Branko. We have just one last question, if you're okay with that.
Yeah.
Yeah, Rob. Go
Hi.
ahead.
Yeah. Thanks for the lecture. My question is a bit naive. It seems more reasonable for me to store the CO2 where the old oil field is instead of pumping it in the deep sea. Because, well, from my impression from the lecture today, it's most of the work seems experimental at a certain stage. So, like, if it's stored in deep sea, wouldn't leakage cause ocean acidification and stuff like that? So potentially catastrophic events like that.
Okay, so maybe let me clarify a little bit. First of all, when we started in early 2000s, thinking about injection of CO2, one of the ideas was to just inject in a very deep sea, actually, where the pressures are such that they will hold the CO2 at the bottom of the sea. But when we talk about offshore, we're actually talking about injection into the subsurface, which has sea above. So that's one thing to clarify first. The second thing, what you asked, is that when we inject the CO2 offshore, we don't have a problem, as I already mentioned, that people are nearby. If there is a catastrophic event, yes, you're right, CO2 may leak, but we may try to fix it there. But we have to count on that. If we don't do this, the current rate of ocean acidification is such that we are already killing a lot of biosphere in there. So one of few catastrophic events would be nothing compared to what we are doing now already.
Thank you.
But all I say, it's possible. I mean, nothing is ideal, right? We have catastrophic events related to nuclear energy, right? This is not to scaremonger around, but this is to be realistic. What is the alternative? The alternative is that we do have ocean acidification and killing a lot of biodiversity there already.
Okay, I think that concludes the questions for today.
Okay, thank you very much for listening to my short lecture and also to a very nice discussion at the end.
Thank you very much for your lecture today.
All the best. Bye.